What do we mean by gravitational field? Well, gravitational field is the acceleration an object will experience at a point in that field, and that acceleration is in meters per second squared. So we measure gravitational field strength in units of acceleration. For an example, the gravitational field strength here on Earth, the surface of the Earth, is 9.8 meters per second squared. If we went out to twice the radius of the Earth, the gravitational field strength would become 1/4 as great due to the inverse square nature of the gravitational force. And we would get gravitational acceleration 1/4 of 9.8 meters per second squared, or 2.45 meters per second squared. The units of gravitational field are the units of acceleration, meters per second squared. What about gravitational flux? What do we mean by gravitational flux? Well, gravitational flux is the product of the gravitational field component, which is perpendicular to the surface, and the surface area. Okay? And what do we mean by that? We mean that, for example, and let me digress from the notes here for a minute. If I want to find the gravitational flux through this cassette box, video cassette box, 8mm video cassette box, let's just say through the top of the box, okay? Gravitational field is 9.8 meters per second squared, straight down. This is the downward direction. You can see when I drop things, okay? So we have a 9.8 meter per second squared acceleration downward, so a 9.8 meter per second squared gravitational field. We multiply that by the area of this thing, and the area of this thing is what, about 0.007 square meters, something like that. Multiply that by the 9.8 meters per second squared, we get the flux through this through the top of this box. Okay, that's what we mean by flux. Now, if I hold the box at an angle, let's say, well, let's do an angle that you can see here, with gravitational field in this direction, then we take the flux to be the component of the gravitational field which is perpendicular to the object and the area. Or, if we wish, the area that's perpendicular to the gravitational field. But that's a little more subtle concept, although it's often more useful. Okay, anyhow, that's what gravitational flux is. If we go to a distance of 2re from the center of the Earth, the flux through a concentric sphere of the radius 2re, that is just a sphere around the Earth that's twice the radius of the Earth. First of all, we know that the gravitational field, gravitational acceleration is perpendicular to that sphere just by the geometry of the sphere and the fact that it's the field is radial with the center of the Earth. And that's going to be just the gravitational field strength then times the area, which is 2.45 meters per second squared times 4 pi times the radius squared. And that's the area of a sphere. This really should be negative. And this flux really is negative. It's inward, not outward, and that will become important later, but I'm not going to make too much of that distinction right now. We'll worry about it when it becomes important. Otherwise, it just seems senseless. The units, of course, are meters per second squared, gravitational field strength times meters squared of area, or meters cubed per second squared. Another example, one of the tabletops here in the lab, the flux through the tabletop. We measured the tabletop and decided that its area was about 1.6 square meters. We multiply that by the field strength and we get the flux. So it's just another flux calculation. Okay, it looks like I've made a couple of revisions to this in the process, but maybe we can read this. What do we mean by the components of a force? Okay, how do we analyze force as a vector? And the idea goes back to the basic principle that we use with any vector quantity. The effect of a force is completely equivalent to the combined effect of its components. A typical example, a 10 Newton force at 30 degrees with respect to the x-axis has components 8.7 newtons in the x direction, 5 newtons in the y direction, as calculated by taking the force times the cosine and then times the sine of this angle. And if we replace the force, the 10 Newton force here, with these two components, again the effect is going to be identical. We can't even feel the difference as we saw in lab, or as we felt in lab with our eyes closed. Okay, the units of force components are of course 0. What do we mean by the components of a velocity vector? Well, again, what's the effect of a velocity vector? Over a time delta t we get a certain displacement. And the displacement that results from a velocity in a given time interval delta t is identical to the sum of the displacement that we get from the components in the same time interval delta t. For example, a velocity of 10 meters per second in direction 30 degrees of the x-axis has components 8.7 and 5 meters per second in the x and y directions respectively. If for 5 seconds we moved at 10 meters per second at 30 degrees, we'd end up 50 meters per second away from our, or 50 meters away from our original point at the angle 30 degrees. If we go 8.7 meters per second times 5 seconds, which is what, 42.5 meters in the x direction and 25 meters in the y direction, we again end up 50 meters from our original point, and at an angular position of 30 degrees with respect to the x-axis. Okay, now returning to questions. We have the question of what are the vector quantities that we study in mechanics. I'm not sure this listing is comprehensive. I didn't go back and make a detailed comparison, but these are the ones that come to mind. If there are any others, please fill them in. But this will give us a pretty good idea of what vector quantities are. Okay, we have displacement delta S. We have a position vector R, which we haven't talked about all that much, although your text has. We have the velocity vector V. These are all quantities that have both magnitude and direction. Acceleration also has a magnitude and a direction. Okay, we have angular displacement, angular velocity, and angular acceleration. These are also vector quantities. Angular displacement in this direction can be associated with a vector perpendicular to the angular displacement. If your fingers move in the direction of the angular displacement, your thumb points in the direction of the vector, so that an angular displacement like this is equivalent to, or is represented by a vector in this direction, as we've discussed and we'll discuss later. An angular velocity and angular acceleration similarly. Okay? And then we have force, which is clearly a vector quantity with magnitude and direction, momentum and torque, and angular momentum. If angular displacement has a direction in space, then angular velocity has the same direction as the corresponding angular displacement. Angular acceleration is not, of course, parallel to angular velocity because it changes angular velocity, but it might be parallel. So angular momentum, which is a product of moment of inertia and angular velocity, is clearly a vector quantity. And things that aren't vectors, time, time interval, work, kinetic energy, potential energy, and power don't have directions.